Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 10 of our electrical machines chapter. That is a chapter 1 transformers. So today we will discuss about exact and approximate equivalent circuit of transformer. So we will discuss the non-idealities. One non-ideality we had already discussed, that is the finite reactance. Okay, we will add the non-idealities, more non-idealities today. Also we will discuss the transformer, the phasor diagram of transformer at different loads. So I had just discussed in if the phasor diagram with lagging load. Now we will discuss the phasor diagram of transformer at different loads. Okay, first point is, first non-ideality is the leakage flux. Okay, what is leakage flux? So leakage flux, right, is the flux that actually does not link both the coils. So that actually does not flow through the core, that flows through outside air. What do I mean? So currently, let's say this flux is flowing, right? Let's say only flux phi m is flowing. So if only flux phi m is flowing, then this phi m, right, once it reaches this point, it has three options. One is to complete the loop here, or go through the core and complete the loop, right? It is just like parallel connection. This is a current of 1 ampere, let's say, or 10 amperes, and I have a resistor here that is of 1 ohms. I have a resistor here that is of 1000 ohms, and I have a resistor here of 1000 ohms. Okay, so what is happening basically? The thing that is happening is that current, somewhat of current will flow through here, right? Because this, of course, current will find its path. I mean, it will choose the least resistance path. That is correct. But bit of current will flow through these two resistance as well. Same is happening here as well. Flux, right, will have three paths. Yes, the reluctance of the air will be much higher than the reluctance of the core, but still some current will flow, right? This 10 amperes will get divided actually. Some of the current, very small amount of current will flow. So this, in same analogy I'm using here, small amount of flux that is actually flowing through the air and that is not linking the secondary. Okay, this flux is not linking the secondary. This flux is only flowing through the air. So this kind of flux is known as leakage flux. Okay, now how do I represent this leakage flux? How do I represent this leakage flux? So it is something like through this coil a current is there, that is going I1 current, correct? And this I1 current is producing some flux phi 1. Now this flux phi 1 is getting divided, so bit of it is going as leakage flux and the rest of it is linking, that is phi m. Okay, same for the coil 2. So if I just draw here that I have a I1 current and I have a inductance like this, right, due to which there is bit of leakage flux. So this is not an actual inductance present in the winding. It is not the actual inductance. It is a fictitious circuit element, fictitious circuit element. I have forgotten the spelling of fictitious. Okay, excuse me, I have forgotten the like the spelling. Just fictitious, I hope you know. Okay, so fictitious element, that it actually does, it is not present in the circuit element, right? It is not actually present here. But for us to model the transformer, we have to take an inductor that actually is producing this amount of flux, because the current is same, right? Same I1 current is flowing for creating the phi 1 flux and for the phi m flux, phi L1 flux and for the phi m flux. So this is known as the air core inductor, that is a fictitious element, not a real element. So due to which some flux is only linking with the primary. Okay, then I have this magnetizing reactance JXM that we already discussed. So this is known as the leakage reactance in the primary. Then I have the magnetizing reactance, and of course after this, right, we have the ideal transformer. Ideal transformer does not have any reactance, right, because it does not require any magnetizing current. So that magnetizing current is actually going through here. Okay, so this is the ideal transformer that is present over here, and again this is the ideal portion. Everything else is non-ideal. So these are the non-idealities, and in the secondary as well, same thing, that I have a leakage reactance in the secondary, and then I have a load connected here. That is totally fine. Okay, okay, so this was about the leakage flux. If of course, why is there leakage? Because this reactance, this reluctance is finite. Reluctance of the core is finite. If let's say the reluctance of the core would have been infinite, if the reluctance of the core would have been infinite, then what would have happened? It is similar to saying that I have this 10 ampere of source here, okay, and the resistance here is 0. Similar, just reluctance is opposite of resistance. So if, sorry, what am I saying? Sorry, reluctance is 0, permeability is infinite. Sorry, so permeability is infinite. Here initially my permeability is finite, mu r is finite, but if I assume my mu r to be infinity, then reluctance will be 0. There will be 0 reluctance. It is same as saying that I have shorted, this resistor value is 0. So it does not matter whatever values of r I place here, some r1, some r2, it does not matter. Whatever value you place, unless and until it is not 0, whole of the current will flow through here only. Why? Because this is short circuit, so here I have 0 drop, so this R2 will also have 0 drop, so 0 divided by R2 will be 0, 0 divided by R1 will be 0 amperes. Okay, so both of them will have 0 drops, 0 current. So all of the current will flow through this wire only. Same thing is happening if the permeability of the core would have been infinite, then there would not have been any leakage flux. Then all of the flux would have flown through the ideal transformer. Then it would have been ideal transformer only. But we know this is not a ideal transformer. Permeability is finite. So of course the current will have different paths to choose from. Okay, current will have different paths to choose from. So yeah, so this was the values, and I hope you have understood this. One of the non-ideality. So this is one of the non-ideality. What is the other non-ideality? So of course I have assumed that this is a winding and this is a wire. So any wire, right? Any wire, if I'm like, this is a wire, if I'm applying some voltage here, V1, I'm measuring the voltage here, V2, of course it will have a resistor. Every wire will have a resistor. That is known as the winding resistance. Winding resistance. So this anyways, I told you in the starting lecture, in the first lecture of transformers, that we were ignoring the winding resistance, but of course it will have a winding resistor. So this will be there. Okay, this winding resistor will be there. So that's how we will model basically our transformer. So this page is not required. This is a waste of a page. So this is my model of the transformer. Just one thing, that XM is there. Okay, one more thing is there for modeling. I have not written it yet. So this right, this is a whole thing only. Yeah? Okay. Okay, what I can do, right, this I can actually copy this. Okay, I need to delete this. Okay, so here, right, what I need to do is I just want to add one thing, that this is my winding resistance. This we have already discussed. This is my input side, this is my secondary side, basically, high voltage, low voltage, whatever you want to say, and in between I have the ideal transformer actually. So ideal transformer is still there. Okay, these are the non-idealities that I had separated out. So ideal transformer is still here. So this is my ideal transformer. So this portion is ideal transformer. Okay, sorry, I know my drawing is pretty bad. So this will be the ideal transformer basically. Okay, so this will be the ideal transformer. This will be the ideal transformer here, and all these are the practical elements. Okay, so that was about the equivalent circuit. With leakage, reactance and everything. Now one more component I will add. What is that component? So this core, right, is actually a electrical element. Okay, this core is made of metal, and metal is conducting, right? Metal is conducting. Okay, just hold on. Metal is conducting. Okay, so if metal is conducting, that means what? That basically means that this current, right, has two paths, one through this metal, one through the winding. Although it does not actually flow through the metal, there are multiple things I will discuss about that. But briefly, roughly, a bit of idea I hope you can get that metal also will act as a conductor. Although they are insulated, yes, I agree. Although they are insulated, but bit of current will flow through this as well. I will discuss how bit of current will flow due to hysteresis and eddy current. Okay, I will discuss about that. Don't worry, I will discuss about that. Okay, so actually, right, this component will have another component added. So there will be a resistance in parallel with this, because that current will not flow through the secondary, right? That current will not go and link the secondary. That current will just flow in this loop. Okay, so there is a division between this winding current and this current. Okay, we will discuss about that. So another practical component that we will add is the resistor Rm. Okay, known as the magnetizing core resistance, RO also sometimes we call it. Okay, or Rm, whatever you want to call, known as the core resistance, whatever you want to call, you can call it. Okay, so there are two components, right? So this, right, is actually, if even though load is not connected, then even though current is zero in IL, so there will be two components of current. One current will be caused due to generation of the flux, that is known as the magnetizing current. Another component is known as the no load coal loss component of the current. Okay, coal loss component of the current, that current is known as the coal loss component of the current. Okay, so just wanted to discuss, like, I forgot to tell this, that there are two kinds of flux. So I should write this as well. There are mainly two kinds. Actually, have I written it here? Yeah, I have already written it, so I don't need to write it. Okay, I don't need to write it. So this, let's clear this one first, that there are two kinds of flux. So already we have cleared it. Let me reiterate it. So there are two kinds of flux. One is leakage flux, another one is magnetizing flux. Okay, so leakage flux is the flux that links with either the primary winding or the secondary winding, but not both, because either it will link only with the primary or it will link only with the secondary. This flux does not contribute to energy transfer between windings and causes leakage reactance. Okay, magnetizing flux is the flux that links both the primary and the secondary winding. Transformer winding resistance. So transformer windings are made of copper. Of course, they will have some finite resistance, although they are very low, but they will have some finite resistance. And if some current flows through the windings, there will be some loss. There will be some copper loss. Okay, so that was about the this thing. So I will just actually place this here only. Okay, so we have discussed about that. Now let's actually discuss about this core loss component. Okay, we will discuss about the core loss component, of course. So whenever there is no load connected here, if there is no load connected, right, so a magnetizing current will be required, that is Im, that will be required to generate the flux phi. Another current will be there due to bit of losses, due to the hysteresis and eddy current loss on the core. Okay, because this will have two paths. So one path it will choose like this, another path will be through the winding Xm. Okay, so that's why there will be a RO, and this will be cleared later on as well. Don't worry, trust me, this will be cleared later on. Okay, so now let us try to draw the exact equivalent circuit. So this is actually the exact equivalent circuit. So you can remember this. What is the exact? Of course, you don't need to remember everything. We have understood conceptually. This is the exact equivalent circuit. Okay, so now let's discuss bit about that core loss component and those things, right? So I will discuss about that core loss component. Let me delete this. We will draw the circuit as well, don't worry. We will draw the phasor diagram as well. This is, why is this here? Okay, already this is added, right? So yeah, this is the equivalent circuit. So we'll discuss about this, right? So this leakage flux and reactance, this already we have discussed. This, like, this is basically saying the same thing. Leakage flux and reactance. Leakage flux is the portion of the magnetic flux that does not link the both the windings, and like my total flux in a winding will consist of the leakage flux that will again come back to the primary winding only, also the phi m, that is the mutual flux. Okay, this we have already discussed, so I don't feel we have to discuss this again. Okay, so like this is the reasoning behind, like the total induced voltage will be due to the mutual voltage. Of course, there are two kinds of flux. One is the leakage flux, another one is the mutual flux. So both will induce a voltage, and due to that voltage, basically there will be a drop. And so this will be the drop due to the leakage flux that we have already discussed, and this will be the induced EMF due to the mutual flux. Due to mutual flux, and this is drop due to the resistance. So that's how we actually write down the equivalent model. So this we have already discussed. I don't think we have to discuss. Okay, so yeah, before coming into this core loss component, basically your core loss component, I mean, this is whatever losses will happen in this, right? These are known as the core loss, or also known as the iron loss. This we will discuss. This let me take it to the next few pages. I will discuss about this later. First, right? Yeah, first let us discuss about this thing. Okay, let us discuss about DC. So if I'm applying a DC, right, if I'm applying a DC here, what will happen? So if I just copy this thing, right, if I apply a DC, everything will get damaged. How everything will get damaged? So if I apply a DC here, like, because now we will discuss DC source with practical transformer, because in practical things will be a bit different. In ideal, we discussed that it will linearly charge, right? That we discuss in the chapter 0 itself. But in this kind of cases, right, in this kind of cases, when I have applied a DC source, what will happen? This reactance will be simply shorted. This reactance will be simply shorted. Okay, this reactance will be simply shorted. This reactance also will be simply shorted. So if I just draw the equivalent circuit, this will be VDC. Okay, and okay, don't forget that I have an ideal transformer here as well, right? I'm just directly connecting it. Actually, there is an ideal transformer in between. Okay, so let me just let me take this. Let me delete all this. Let me copy this. Let me make this here only. So this is for the practical transformer. Okay, so if VDC is there, of course this will act as a short circuit. This will behave as a short circuit. This also will be behaving as a short circuit only. Okay, so all of this is shorted. So what is my equivalent circuit? So my equivalent circuit is something like this. I have a R1 resistance here, and it is shorted. So it will not, no current will flow through here because this is shorted. So this is my VDC. So that's why they say that my transformer winding will burn. Transformer will burn if I apply a DC, right? Even though it is practical, it will be, what will be the current? VDC by R1, and I know my R1 is very small. Okay, if R1 is very small, basically my current I1 will be very large. Okay, it will be very high amount of current. It will be very high amount of current. Okay, so if it is very high amount of current, so what I can comment is very high amount of current will flow. So the winding can get damaged. Winding can get burned because there will be huge amount of loss I1 square R, and that will produce heat, and due to heat, winding will get damaged. So that's why they say that winding will get damaged. Okay, I have told you all the cases. If it is practical, if it is ideal, all the cases. Whenever DC is there, try to solve with fundamental. Don't use any formula or tricks. Don't remember the things. Okay, try to solve fundamentally. Okay, so that was about the this core loss. Actually, I should have taken this no load current earlier actually. So I will discuss about this no load current, right? We'll discuss about the no load current. I will take this no load current earlier here. So yeah, that is actually here. So let me take it right now. After that, we will discuss few other things. Let me take it here. This is here. Yeah, this is here only. Okay, this should be actually here. Yeah, now it is fine. So yeah, it is fine. It is fine. So yes, it is fine. No, I'm just checking because my flow is bit broken. This is not, yeah, this is not required. Okay, so now let's discuss about this core loss component, the no load component, basically this one. Okay, so transformer at no load, the secondary winding is open circuited, then there is no current in the secondary winding, so current is zero. The primary winding, when connected to a voltage source, draws a magnetizing current to establish the core flux that we have discussed. The transformer behaves similarly as inductor, so the current lags the voltage by 90 degrees. But there are two components. So one is known as the magnetizing component. Okay, another one component. So this current, right, when the output is open circuited, is known as the no load current or exciting current. No load or exciting current. Okay, so this has two components. One is magnetizing current, another one is core loss component. Magnetizing we have already discussed. Core loss is amount for the core loss, iron losses including hysteresis and the eddy current. This actually causes power loss in the transformer. There is a real power lost in the transformer, but this, right, does not cause no power loss. This is used for what? This is used actually for generating the flux, so no power loss here. So that's why it is called as what, this component is called as what full component. This component is called as whatless, because actually there is no power loss here. What is happening, the current that I needed, this was used to generate the flux. There is no power loss, but there is power loss here. That's why it is called as what full component. Okay, so this we will discuss when we will discuss about losses, that why this occur. So core loss component of current denoted by IW, generally it is denoted by IW, represents the portion of no load current that accounts for core or iron loss in the transformer. These losses occur due to applying an alternating magnetic field in the core. So if I apply any alternating magnetic field in the core, if there is some alternating magnetic field in the core, there is some hysteresis loss, because every time the magnetic field phi will increase in this direction and then reduce, there will be hysteresis. What is hysteresis? We have discussed very well, right? And if whenever there is time varying flux in the core, right, due to that, what will happen inside the core itself, in a very small region, small area if I choose, there is time varying flux here, phi t. So due to this time varying flux, what will happen is that there will be d phi by dt, because this is not constant, so it will induce a voltage. So in this loop itself, a voltage will be induced, that is known as the eddy voltage. So due to this eddy voltage divided by the loop resistance, E eddy divided by the loop resistance, a current will flow. Okay, R loop. So that current will actually cause bit of loss, I eddy. So this eddy current will cause bit of loss. Okay, so it is I eddy whole square, I eddy whole square into R. I eddy whole square into R. That's it basically. That's it. Okay, I hope you have understood this point. So yeah, that was about this core loss component. So this core loss has two components, hysteresis loss and an eddy current loss. This formula you can ignore for now. We will discuss about this formula. Just two things you need to keep in mind. At that point of time also I will discuss, but I am discussing now itself, that here the BM, right, is due to what? This BM is the flux due to the induced voltage. Like, sorry, I told you opposite. The whatever flux is getting generated, that helps in generating the induced voltage. So E1 and E2, it is not my supply voltage, because now we are talking about practical transformer. So in practical transformer, the induced voltage is here. Actually, sorry, this E1 should be here actually, sorry. Induced voltage is here, right? So here also I missed a point, that induced voltage will not be here actually, sorry. Induced voltage will be here. So in case of A, practical transformer, the induced voltage and the supply voltage, output voltage are not actually same. So here also induced voltage is here, okay, E2 dash. Actually, this will be E2 dash only because I've referred this to the, okay, that time I referred it to the primary, okay. This we can write as E2 only, E2, E2. We are not referring anything. Otherwise, it will cause confusion. I don't want you to cause confusion. Okay. So, yeah. So, this is not E2 dash, simply V2, right? I'm not referring anything. So, this time, right, my induced voltage and supply voltage are not same. So, that's why please keep this in mind. This flux, whatever this flux, time varying flux is there, this will be responsible for the induced voltage. How do I find out then V1 and E1? So, V1 will be equals to E1 plus J I1 into XL1 and plus I1 into R1, and of course that magnetizing component is there. That this is anyways in parallel, right? This does not matter. This is anyways in parallel, so it does not matter. The drop across this R and L, whatever the drop across this R and L, that will be the only problem. This R and L. So if I take the drop across this R and L, I will get back my E1 voltage. If I place it here or here, it does not matter. It is in parallel, right? So it does not matter. Same for V2. So how will I find V2? So V2 will be equals to, what is V2? So V2 will be equals to basically E2, and there is a drop, right? If I see there is a drop in R2 and X2, so E2 will be higher because it is supplying to the load. So it will be higher. So it will be E2 minus J I2 XL2 leakage reactance minus J I2 R2. Okay, that will be my E2 equals to. That was about it. Now how do I find out the core loss? This whole hysteresis, like this whole can be written as P core, right? My P core consists of the hysteresis loss. P core will consist of the hysteresis loss plus the eddy current loss. Okay, so P core will consist of the hysteresis loss and the eddy current loss. So this, right, will be the which will cause the loss. This, right, this component will cause the loss basically. Where is the equivalent circuit? 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 Okay, I have to find it. It is here. Okay. So this will be here. So now I can say that my which will cause the loss? Only this will cause the loss, right? This is just purely imaginary. This will not cause the loss. So the loss, P core loss, will be due to E1 whole square divided by RO. Okay, that will be the P core loss. Generally, what we do is approximately, again I will make few approximations. I will discuss about that. So actually P core loss is E1 square divided by RO. We will make few approximations. So what kind of approximations we will make? So what we will do, right? We'll actually shift the circuit into the right hand side. We will shift the circuit in the right hand side. Why? So now we are discussing about, like, this is the actual equivalent circuit of the transformer. Okay. So this is also one of the way to write the transformer, right? So what we did, we removed the ideal transformer. We directly referred this voltage in the primary. So this E2 will become E2 dash, V2 will become V2 dash, every component will become dash, referred component. So whenever there is a dash, so R2 dash, XL2 dash, E2 dash, my V2 dash, all these are referred to the primary. So I don't have to wire, I don't have to draw the transformer. You can draw the transformer, but to avoid drawing the transformer directly, I can write it like this. So all these are referred quantities. Okay, so previously I was not referring, now I have referred. Okay, now what we do, this is my equivalent circuit because I have to do few analysis. To do the analysis, we will do this. So I will actually approximate it. So before going into the approximation, let's solve this very interesting thing, that let's say if I have these components of resistance and these are arranged like this, okay, three of this. Now I have this Zn is here, 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 okay. So what I can say is what will be the input impedance in the first case, second case and the third case. Let us calculate. So Zn in the first case will be what? It will be 0.1 plus 1000 into 0.2 divided by 1000.2. Okay, so this value will be Zn will be equals to this will value will write this value will be 1000 into 0.2 divided by 1000.2 plus 0.1. So this will be almost 0.299, okay, almost 0.299 ohms. What about the second case? This was the first case. Second case it will be Zn will be equals to 1000 in parallel with this 0.3 divided by 0.3. So it is 1000 into 0.3 divided by 1000.3. It is also almost equals to 0.299. And here as well, if I see in the third case Zn, it will be 0.3, and this is sorted, right? This point is sorted, so I'm just sorting this point. This point is basically sorted. I like what am I doing? First, this is the actual circuit. Then what I'm doing, I'm moving this point 1 in the right hand side, and then I'm moving this point 2 in the left hand side. Okay, hold from here to the left hand side. So I just want to see how much of a difference it makes. So this will be what? This will be simply 0.3 only, because this is shorted. So this will be 0.3 ohms only. So if you are observing that there is very little difference, right? If I move it, if I have a high impedance parallel, if I have a element that is very high resistance or impedance connected in parallel, it will not make much of a difference. So actually this Rm is generally very high value, very large value, because the no load component of the current will be very low value. Okay, core losses are there, but that is very low. So this Rm will be very large. So if this Rm is very large, and for our own convenience, we can actually draw the circuit in a different manner. Okay, we can approximate it. How can I approximate? So there are two ways to approximate. So first way is, if I move this whole thing on the left hand side, so this parallel branch can be moved in on the right hand side basically, and this whole thing will be there on the left hand side. Okay, so this, right, what we can do, okay, this I can copy and paste, and this I can, okay, no, this will not work. I don't actually, do I actually need it? I don't need it actually. Okay, this whole thing can go on the right hand side basically, or whole thing can go on the left hand side. So okay, so this whole thing I can copy. Okay, so this whole thing will be here. Okay, and after that the load will be there. So I just shifted this R to X2 on the left hand side. Will that make any difference? No, I have proven it to you, it will not make any difference. I mean, it will make a difference, of course it will make a difference, but the difference will be very minuscule. Okay, same thing I can do if I want to move everything on the left hand side. So what I can do, right? Okay, let me copy this. So this whole thing can go on the left hand side actually. So load will be still here, this will not be here, this will be shifted actually, this will be here only. This will be here only. Okay, and here. totally shift this circuit here. Okay, so both ways it will not matter much. Okay, it will not make any difference because IO current is very low. IO current is very low. So we can approximate our circuit like this. Okay, so there are two models, and in approximate equivalent circuit, core loss and the magnetizing current, sorry, the current in the RM branch will be overestimated. Why it will be overestimated? Because we are not assuming any drop. So E1, right? In this case, there will not be any drop in E1, right? So V1 will be equals to E1. So in the actual circuit, in the actual exact circuit, I know that V1 is not equals to E1. So the core loss actually is E1 whole square divided by RM or RO, whatever you want to call. So, but here, right? But V1 is higher than E1 because there is a bit of drop here. So of course, V1 whole square divided by RM will be greater than E1 whole square divided by RM. So core loss is this value, actual core loss. But here, right? If I take this circuit, then what is the core loss? The core loss here will be overestimated. Why? Because V1 is E1. So my P core will be equals to V1 whole square divided by RM. So core loss will be overestimated. Core loss will be overestimated. That is, I will write here. So my current also, the core loss component current will also be overestimated. Core loss component and the P core loss component of the current and the core loss component of the current and the core loss both will be overestimated. Got it? So this will happen in this approximate model. Okay, there are many models. So, and in the first one, what will happen? Actually here, right, the core loss will be underestimated. Here the core loss will be underestimated. If you see, because here, right, there is more drop in E1, right? This also resistance are there, so there will be more drop. So here the P core and the IC or IO, whatever you want to call, will be underestimated. So, but it will not make much of a, like, there will not be very high percentage difference, right? If let's say the core loss is 50 watts actual, then it will be like 49.8 watts in the approximate model. So that is totally fine because the calculation is very tough. If you want to solve this exact model, right, calculation will be very difficult. So of course we don't solve the exact model, we solve the approximate model. So underestimated. Okay, so yeah, I hope you have understood this basic point. So now let's draw a bit of this phasor diagram. Okay, let's draw a phasor diagram of the uh, approximate circuit. Okay, actual circuit we have already drawn. Let's draw the phasor diagram of approximate circuit. So there are two ways to solve. So this, right, this, let's solve it for this one. So if I solve it if I draw the phasor diagram for this, what is happening is my drop is what? So this, right, this can be combined in a single resistance value. So this is a single resistance value. Let's write the resistance value as RO1, total resistance in the winding one, whatever I am observing, and a single inductance value, that is X. This is actually XL1, this should be XL2. So this will be XO1, XLO1. Okay, and of course there is a leakage reactance here and the core resistance here. Okay, and this is my E2 dash. Basically E2 dash, E1 are both are same only. So can you draw the phasor diagram? So this is my V1, this is my induced EMF E1. Okay, in these 2 points, can you draw the phasor diagram? So if I just copy the ideal phasor diagram, where is the ideal phasor diagram? If I can somehow, okay, I will not be able to find it. I have to go real back. I have to go. Okay, how much back? That is the main question. How much back do we have to go? Okay, this is actually, okay, this is good enough. We'll copy this. Okay, where is the magnetizing current here? Magnetizing current automatically uh, got over. How is it possible? How is the magnetizing current over? That is not possible, no. So something is wrong here. This flux will be here. Actually, somehow it got deleted, I guess. Okay. So this value will be where is the approximate model? Here I am. Yes, here I am. Okay, so if I just paste this phasor diagram, so this load currents I will remove. For now we are considering without load. So the actually now the current, right, no load current will have two components. One is the magnetizing component, the wattful component. So this current is parallel to E1. Okay, this current is parallel to E1, but I am showing currents in the primary. Okay, I am showing currents in the primary, so I will show currents in this direction. I hope you understand. I hope you understand this point, that because I am showing current in the primary, okay, and this is I1 into, like, drop I1, sorry, this is E1 divided by Rm, so this is the current, right? E1 divided by Rm, E1 divided by Rm. So okay, although you will say that, sir, this drop is across this Rm, right? But some current is flowing, so here I have some current, that is IC core current, and this is I magnetizing current. Okay, so magnetizing current is here, no doubt. Magnetizing current is here, no doubt, no problem with that. What about this no load core loss component of current? Yeah, sorry for the interruption, my recording suddenly got stopped. So as I was saying, like, where will this core loss component of the current be? IC. So this IC, right, will be actually along the V1 only. Okay, this only one thing I will tell you to remember, because the phasor diagram, right, is just there for show. Actually, because it is just there for representation. Actually, we will not use the phasor diagram much. In transformer, you will say they will not use the phasor diagram. So this current core loss component of the current will be along the V1 only, IW or IC, whatever you want to write. Okay, so this is my magnetizing component. This is my core loss component. Okay, so what will be the IO? IO will be the vector sum of IC and IM, or IW or IM. So this will be here, right? This will be the no load current IO. Okay, now what about the other components of current? So other components of current, for now we have not discussed. So what will be the actual E1? What will be the value of E1 actually? What will be the value of E1? Now we have winding resistance, right? So it is not that simple. It is not that simple anymore. Okay, so E1, right, there will be bit of drop in the E1. So this V1, right, is a sum of the drop across this R1 and JXL1. Okay, so your E1, actually my E1 is in this direction only, right? Actually my E1 is in this direction if it is ideal transformer, but we had shown it here just to show that it is opposing. It is opposing in nature. That's it. That's it. Okay, so actually if I know my flux is here and my current I1, what will be my current I1? So I have to find out the current I1. So my V1 is here. Okay, and my E1 will be here only, because E1 will always, there will be 90-degree phase shift between E1 and phi. Okay, so there will be a bit of drop in with I1. Okay, so I'm solving this circuit. So my E1 is here basically, right? Basically what is the thing? The thing is my V1, phasor V1 is equals to E1 phasor plus R1 plus j omega L1, or like XL1 into I1 phasor. That is the value. What is I1? I1 phasor is equals to IO plus I2 dash. Correct? So IO is here. What is I2 dash? So let's assume for a second, let's assume that our load is lagging. Okay, so for a second let's assume that our load is actually lagging. So if our load is lagging, then if my, let's assume that my V2 will be somewhere here, right? So if my load is lagging and my so V2 and E2 dash are same, right? That is what we have approximated. V2 and E2 dash are same. That is our approximation. So if V2 dash and E2 dash are same, so this will also be equals to V2 dash only. This will also be equals to V2 dash only. Okay, so now what about the other portion? The other portion is, what about current I2? The current I2, it's a lagging circuit, so it will lag the voltage and it will lie somewhere around here. Okay, this will be the I2 current. But I have to add I2 dash. This is I2 dash. So I2 dash will be in phase opposition with I2. Correct? I2 dash will be in phase opposition with I2. So it will be somewhere here. It will be exactly somewhere here. This will be my I2 dash. Of course, there is multiplication of N2 by N1 that you can do, right? MMF balance. Now I will add I2 dash and IO to get I1. So I will add I2 dash and IO. Right? This will be I2 dash and IO basically. So it will be somewhere around here. Okay. So IO is somewhere around here. So this is my I2 current. This is my I2 current. Okay. So this is my I2. So not I2. Sorry, this is my I1 current, right? Sum of both IO and I2. From here, actually, we will be able to plot the V1 actually. From here, actually, we should have started with E2 V2 dash only. So if we started with E2 V2, because V1 will not be exactly here, right? So what is happening? I1 is in this direction. So the drop, that is I1 R1, will also be in this direction, correct? In the same direction. The drop I1 R1, because it will be in phase with the current and voltage. So this will be the drop, that is I1 R1. Okay. What about the drop? This drop, right? This will be 90-degree leading with respect to I1. So this will be the drop across the leakage reactance. So leakage reactance drop will be here. This will be j omega I1 into L1. Okay. And my E1 is like, although I have shown it here, E1 is somewhere here, right? Somewhere here. Originally E1 is somewhere here. So this will be sum of this two drops and this E1, correct? So actually it will lie somewhere around here. Okay, although the diagram is a bit messy. Okay, I have to change the color here. Oh my god, this is going super messy. Okay, not that messy. So okay, I have to change this color as well. This is also clashing. I am running out of color, guys. Please suggest me any colors in the comment section. Okay, so this also will be this color. So what is happening basically, there are two drops, this I1 R1 and j omega x1, and although I have shown E1 here, but actually originally E1 should be here only, right? Originally E1 should be here only, correct? So it is a vector sum of E1 and this drop. So this is the drop and this is E1 basically. So what will be my V1? V1 will be basically addition of these two vectors. So how do I add these two? Okay, so it will be basically like, this is the resultant drop, right? This is the resultant drop basically. If I show you that this is my resultant drop, correct? Resultant drop. So overall this will be the vector sum. So this will be the resultant here. Okay, and this should have been a bit bigger. Actually I should show it a bit bigger. So this will be here and here and here. So this will be my actual V1, correct? So we went backward actually. What we did is, we know the load and E2 is equals to V2. So if E2 is equals to V2, I know the current I2 will lag because we have assumed it as a lagging load. We have assumed the current as a lagging load. Okay. So if we have assumed it as a lagging load, that means I2 will be here, then I2 dash will be in the opposite direction, and from there I had find out the drop, and from there I solved it. Okay, I know that this is messy. Please rewatch it again. So this is the power factor angle phi 2. Okay, and this is the supply power factor basically. V1 is here and I1 is here. So the supply power factor will be this phi 1. Okay, power factor on the input side. Okay, I hope you have understood this point. So basically if you see, the phi 1 is greater than phi 2. So that is also not phi 1 is greater than phi 2. One more comparison I want to do. This angle, right, between the magnetizing current and the no load current, no load exciting current, is angle known as phi 0. And generally your phi 0 will be very low than phi 1. Why it will be very low? Because like mostly it is the magnetizing component of the current. This no load, this coal loss component is very low. Okay, so mostly it is dominated by the IM. So that's why the resultant will be inclined more towards here. So phi O will be less than phi 1. So basically my cos phi 0 will be greater than cos phi 1. Okay, that's it. That's it basically. So yeah. So this is one, so not cos phi 0, sorry, yeah, am I correct? Cos phi O phi 0 is no dot component of the, sorry, I'm measuring this angle wrong, sorry, I'm really sorry. So phi 0, right, is the angle between the voltage V1 supply voltage and the no load component of current. So this is actually the phi 0. So there are so many colors here, I'm sorry for this messy, for this being being this messy. Okay, I'm really sorry. So okay, it will be here between the voltage. So phi 0 is the angle between the voltage and the supply voltage. So this is the angle between V1 and the no load component of current, and phi 1 is the angle between the uh, voltage and the supply current. Phi 2 is the angle between the secondary voltage, secondary not induced, the actual voltage. In this case it is equal because it is approximate circuit, V2 and the secondary current. Okay, so these are the three components basically. So this is the phasor diagram. Okay, I know it's a bit messy, so what I will do, I will enlarge this. So if I enlarge this, right, it will be a bit more easier for you to understand. If I enlarge this thing, bit more easier for you to understand. So yeah, so the homework for you is solve for this one, draw the phasor diagram for this one. This is the homework. Okay, I will not do everything, I will leave out few things for you as well. So same thing now, what will be the difference? The difference will be that this time my V1 and E1 will be equal. Previously my V2 dash and E2 dash, V2 dash and E2 dash were equal, but now my V1 and E1 will be equal. Okay, so that is one thing. My E2 dash will be here, my E2 dash will be here, this R1 will be on the right hand side, so this I can shift a bit on the left side. My E2 dash and V2 dash will not be equal anymore. Okay, I1 will be here only, I1 will not change, it will be here only. Okay, so that is the value over here, that is the value over here. I hope you have understood this point. Okay, so this was the homework, this is the homework. So just make V1 equals C1 and rest other things will be following. Okay, rest other things you can follow. So I guess we are done with this approximate analysis and hysteresis loss. We will discuss about the formulas, don't worry, we will discuss about all these formulas later on, don't worry. I'm just wanted to specify few things like why this coal loss component comes and those things. Okay, so now let's draw a phasor diagram if I have load connected. Okay, if I have a ideal, like let's assume that it is kind of ideal only. If it is kind of ideal only, so mainly, right, these drops we don't consider. So while drawing the phasor diagram, while drawing the transformer phasor diagram, we never consider these drops, I omega L1 I1 to R1. Generally we ignore it, okay, because these are very low values, but I had to explain you the concept, that's why I have written it. But generally while drawing the phasor diagram, like you can see, right, how much messy this is, right? So we generally ignore this actually. So generally, right, if I have this loads, this, let me delete, these pages are not there for any use, so this page is, let me delete. Okay, so power flow in no load, so in no load, right, there are mainly this, I should add earlier note here, this is wrong, yeah, here. So in no load basically there are two powers, one is the active power, another one is the reactive power. So in the starting itself, I have told you that why is reactive power important in network theory as well. In AC analysis, I have told you that reactive power is actually important to maintain the flux, to produce the flux, because flux will link the secondary. So that is why reactive power is important. Okay, and what is active power? Active power is used to compensate for the coal losses. what are the core losses? Hysteresis and eddy current loss. So this is the watt full component. The active energy that is required to compensate these losses are known as the active power that will be required in no load condition. And in no load condition, reactive power is the power that is required to maintain the flux. Okay, it is not like some active power is getting consumed there. No, it is the power that is required to maintain the flux, and we have discussed about reactive power very well in AC analysis. So I am not explaining you here. Okay, so no load component, two components will be there: magnetizing current, core loss component. Okay, so no load power factor generally will be very low because my phi O will be very high. It will be very close to almost 80 to 75 degrees. Okay, so cos phi O will be very low since magnetizing current will be dominating. The core loss component will be very low. In practically, you will measure the values. You will see the core loss component current is very low. It is like 20% of the magnetizing component, something like that. Okay, so that was it. I hope you have understood this point. So now let's discuss this thing. Let's discuss about this, that what is my, like, what will happen in resistive load. So if it's a resistive load, my E2 is here, assumption is my V2 is also same only. So if it's a resistive load, like this is my transformer, and for a second my assumption is that transformer, the leakage reactance and the winding resistance I am ignoring for a second. For a second I am ignoring the leakage reactance and winding resistance. So I am just drawing the parallel branch. So this will be my RM and Jackson. Okay, and here I will have a voltage V1 and V2. Okay, so here I have a no load component of the current, that is IO. So now if I want to measure the currents and voltages, right? So basically this IO will have, now if you see this, like now I hope you will understand that this is my IO current here, this is my induced EMF E2 here. Okay, so actually this will get clear now. Why am I writing this IC along RM? So this IC is what? V1 by RM. So that's why it will be along this here, right? So this is not E2, this is E1. That's why this IC will be along the V1. Okay, and this E1, just I have to represent this E1 here because, just hold on, this E1 is actually in the opposite, like it's in the phase opposition, it is opposing the initial voltage. So that's why this is here. Okay, so IC is here, IM will be along the flux direction, so here, and my core loss component of the current will be here. IU. Okay, and this will be my phi O basically. And what about if the load is purely resistive? So if the load is purely resistive, that means in the secondary, this is my V2, this is my E2, and this is my load RL, whatever this is. So V2 and E2 are both in same phase basically. So like it will be in the same phase only. So my current I2 will be in the same phase as E2 only. So this will be my I2 current. So what will be I2 dash? So here, right, I will have I2 dash. So what will be the I2 dash? I2 dash will be in the opposite direction. So it will be in this direction. It will be in the opposite direction. And what will be the current? Like summation of the current. So it will be summation of the IO current and the I2 dash current. Okay. So it will be here, that is I1 current, right? So I1 current is here. It is the summation of I2 dash and IO. So I1 current is here, so this is the phase angle between V1 and I1, that is phi 1. So that's how you draw the phasor diagram. So you don't actually show the winding resistance drop, okay? Else it will become very hectic. So same thing I will do for a inductive load. If I have an inductive load, what will be the phasor diagram? So slightly things will be different. I will just copy this, okay? That will be easier for me. So this I will delete. Okay, so let me paste this here. Let me delete this. So this time my I2 dash will change. So IO will not change, obviously. IO is like fixed component, right? IO will not change. So this will change actually. My I2 will change. If it's a inductive load, that means what? My like if it's a inductive load, right? It is not purely inductive. It is an inductive load. That means it is, let's say, a combination of R and L. Correct? So current will be lagging the voltage. So I2, like this we have already done previously as well. So current will be somewhere here, right? It will lag the voltage by what will be the phase angle? Let's assume that this is Z angle of phi 2. Okay, so this phase angle will be phi 2 between E2 and the current I2. Okay, what will be I2 dash? I2 dash will be just in the phase opposition, 180 degree phase opposition. This will be I2 dash. Okay, now we will add the two things. So we will add the no load current and the I2 dash. So now this will be here. Okay, so my I1 current will be here. Okay, so this will be my I1 current, and now the phase angle will further increase. If you see, the phase angle has further increased, that is phi 1. Okay, what about the this last load? So for capacitive load, everything will be similar, right? For capacitive load, everything will be almost similar. Just this time, the current will be leading. The load current will be leading the load voltage. So this will be a RC circuit. So if this is a RC circuit, this will be, here I will have a C. Okay, and my phi z will be negative now. It will not be a positive number, it will be a negative number. Okay, so basically the I2 current, I will delete this I2 dash, I will delete this I1. All this we don't need. So this time my I2 will lead the voltage. So I will lead the induced voltage. So I will lie somewhere around here. This will be my I2 and this will be my phi 2. And as I am leading, so the opposite of I2 will be lying somewhere around here. This will be my I2 dash. So the sum of these two will be somewhat like this. This will be my IO. Okay, and basically IO can go here as well, it can go here as well, depending, because transformer in itself is a lagging load. Transformer is a lagging load and capacitive load I'm giving. So this time my the angle actually will reduce, phase angle will reduce than the previous case. So IO will be somewhere around here, not IO, sorry, I1. I1 will be somewhere around here, and this will be the angle now, phi 1. So if you observe that the phi 1 angle has reduced, so previously it was more, here it has reduced, and for resistive it will be less than this inductive case, because of course if it is more like inductive, it will be lagging more. So that's why the angle is more increasing, because transformer in itself is a lagging load. Transformer in itself is a lagging load. Okay, so yeah, that is what you need to understand. Like these are the phasor diagrams, basic phasor diagrams you should know, and we are able to plot it. So of course we are not taking into effect the drop. If I take effect of the drop, things will be more complex, so we don't want to do that. Okay, we don't want to do that. So I hope you have understood this question. So there are a few interview questions that you should actually go through, and in this whole course we will discuss about interview questions as well. So that once you will go after your gate preparation, right, you will apply for jobs. There will be interviews for BARC, for any different kind of PSUs. There they will ask all these interview questions. So that's why in this course everything will be covered, from interview to the written test. Every single thing will be covered. So why transformer is a constant flux device, which we already have discussed, that since we apply V1 voltage, so keeping, if I fix my V1 at a fixed frequency, phi m will be fixed. How? You can prove it with the equation. So we already know that my phi m will be Vm, or sorry, Vrms uh, divided by root 2 pi f n, right? This we already know. This we have already proved. So same thing, right? Same thing is here only. So if these are fixed, then my maximum flux also will be fixed. That's how the transformer is a constant flux device. Constant flux meaning it is telling me that the peak value of flux is will be constant. Peak value will be constant. Okay, it is not telling that flux will be totally constant. No, flux is a time varying quantity only, because if flux is not time varying, then how am I differentiating flux and getting some finite value induced voltage? That is not possible, right? So you have to explain this to the interviewer. How does the primary compensate for secondary flux? By increasing its own current. So previously the primary was taking only the magnetizing component of current. Now it increased from Im to Im plus I1 dash. Okay, that is a I1 dash current. Why is MMF balance necessary? Why is MMF balance necessary? Without MMF balance, the core flux would fluctuate, leading to saturation and inefficient operation. Of course, core flux is fixed actually. So this is linked with the first question. So core flux is fixed. So if it is fixed, of course, it should not change. That's why there is MMF balance necessary. That's why MMF balance is necessary. Okay. So I hope you have understood these basic points. So like, let's say if you by any chance had to plot this voltage, this drop, right? How else we could have done it actually? This, right? This phasor diagram. How else we could have done it? So the better way would be I1 current, if you are able to find out. Yes, I1 I will be able to. So the best way to draw the phasor diagram. Okay, best way to draw the phasor diagram, I will explain you. Okay, so let's take the exact analysis. So I'm drawing the equivalent circuit only, phasor diagram, approximate phasor diagram. Okay, with the most easiest method. So if I have the phasor, if I have the circuit diagram here, and so initial phasor diagram is this only, correct? This will be always correct. This will be always there. So supply voltage actually won't be there. Supply voltage won't be there. Induced voltage I will start with. Okay, so all this will be gone. This IO current will be always there. IO current, IC current, this will be always there. This I2 I will start. So initially I have this induced E1 voltage and E2 voltage. That this much I know. So if E2 is here, how will I find out V2? So V2 will be what? So E2 will be equals to the V2 dash phasor plus I2 dash into R2 dash plus J X2 dash. Okay, this will be V2 dash. Okay, this will be V2 dash. So my V2 dash will be this value. So what is my V2 dash actually? V2 dash is equals to E2 dash minus I2 dash into R2 plus JX2. So where will I2 lie actually? So I2, let's assume I2 is lagging load. So if I2 is lagging load, so I2 will be lagging somewhere. So I2, assumption is I2 is lagging load, so it will anyways lag the voltage. So I2 will be lying somewhere around here. Actually it will be lagging with respect to the V2 only. We will calculate the V2 later on. Let's first write the I2. For now this is I2 dash only. Okay, let's first, then this is I2 only. Okay, so I2 is a lagging load. Okay, so and let me take this, this is not exactly correct actually. So because let us not use the referred impedances, else you will get confused again. I don't want you to get confused. Okay, so let me actually bring that circuit. That circuit will be the best, else you will get confused. So where is the circuit? Yeah, this is the circuit. Yeah, so this is the exact equivalent circuit that will copy. So this actually will plot. We will not plot that one, else you will get confused. I don't want you to get confused. So here, right? I don't have dash, nothing is deferred here. Okay, so this is not okay, dash are gone, all the dashes are gone. Okay, so assumption is that it is a lagging load. If it is a lagging load, of course I2 will lag E1 and E2. It will lag E1 and E2. This much I know. Okay, so if I2 is here, then what will be I2 into R2? I2 into R2 will be in the same direction, but I have to subtract it from E1. So I have to, not E1, sorry, I have to subtract it from E2. How will I subtract? So I2 R2, I2 R2 will be in this direction, right? I2 R2 will be in this direction. This will be the direction of I2 R2, parallel of I2, because R2 is just a constant number. If I multiply R2 with I2, it will be parallel, right? But what I have to do in the equation, if you see, I have to subtract, like this is E2 bar minus I2 R2. So I have to subtract I2 R2. So this is plus I2 R2, but I actually need to, basically this is vector addition, right? So I can rewrite this that it is E2 plus minus of I2 R2. So I will rewrite this. So instead of writing plus I2 R2, I have to add minus of I2 R2. So minus of I2 R2 will be in the phase opposition, correct? It will be here, exactly 180-degree phase apart. It will be minus I2 R2. So this component, this vector I have to add with E2. Okay, got it. Same thing I have to do for x2 as well, right? Jx2. So what is I2 Jx2? I2 Jx2 will be 90-degree component that will lag the that is plus j into x2. So it is, if it is plus j into x2, that means plus j means I will go in the anti-clockwise direction, and this is minus j into x2. If it is minus j into x2, so I will go in the clockwise direction. I will go in the I will go in the anti-clockwise direction, right? If it is minus j into x2, I will go in the anti-clockwise direction. No, sorry, what I mean. So sorry, this is I2 into x2, right? So now this will be minus of j I2 into x2. So what is plus j of I2 into x2? Plus j of I2 into x2, from this point it will be in the, like this is my actually direction, and I have to add another extra 90 degrees. So if I have to add another extra 90 degrees, I will be in this direction, right? So adding angle means I will move in the clockwise direction. Adding positive angle means I will move in the clockwise direction. So this will be minus I2, sorry, this will be plus j I2 into x2. Okay, now what about here? So here, right, actually it is minus j, so it will be phase opposition. So here also it will be in phase opposition only. So this will be the value will be minus j I2 into x2. Okay, so this will be the phase opposition basically. So my v1 will be what? V1 will be this addition. So ultimately v1 will be this value. V1 will be this value. So this will be my actually v1. Okay, so not v1, sorry, v2. So I hope you understood that point. Now if I go in the opposite direction, so with v2 I will add I2 x2 and I will add I2 r2. So I will get back e2. Okay, going in the opposite direction. So if you go in the opposite direction, you will get back the same value. So this is my v2, and ultimately this is actually my phi2. This is actually my phi2. Okay, so like this you can find out. Now this is my I2. So what will be my, like I am just telling you another alternative way to draw the phasor diagram. Okay, there are many ways to draw the phasor diagram. Now what is with winding resistance? With winding resistance and leakage resistance, how will you draw the phasor diagram? So I2 dash, because my I1 is I2 dash plus I0. So I2 dash will be somewhere here, minus, like it will be in the opposite direction, right? So it will be somewhere here. correct? This is my I2 dash. Okay, so what will be my I1? So I1 will be the addition of I2 dash and IO. So IO is here, so it will be addition of I2 dash and IO. Okay, so this is my I1. Now I have got my I1. So what is my V1? V1 will be E1 plus I1 R1 plus J I1 X1. Okay, so this is my I1. Okay, so this is my I1. Now I have to add I1 R1. I1 R1 will be what? Like with respect to, I have to add with E1. So E1 is here. So actually E1 is here, remember, but I will write here E1 fictitious E1, right? So E1 will be here only. So with respect to this only we will add. With respect to this only we will add. Okay, because my E1 is actually in phase opposition. So we have to add with minus E1. Remember this. This E1 is shown here in phase opposition in the phasor diagram. So E1 is, this is the E1 fictitious E1. So I will add this with I1 R1. So I1 R1 will be just parallel of I1 only. Okay, then I will add JI1 X1. So JI1 will be in 90 degree in the anti-clockwise direction because I'm adding 90 degree angle. So this will be, what are the colors? JI1 X1. Okay, so what will be my V2 basically? So my V2 will be this value. Okay, actually this JI1 X1 is more big. Okay, so generally V2 lags more actually. Okay, so my V1, right? If I have any good color left, so V1 will be this. This will be my V1. Got it? So I do understand there might be a bit of confusion at the starting of this lecture. So if you just keep watching the lecture, right, it should get automatically cleared as you watch the lectures. So this is another way how you can draw the phasor. So this angle will be the phi 1, angle between the current and the voltage. Okay, so this angle is the phi 1. So now we can move on to another another kind of problem, the winding resistance. So what is the winding resistance referred to the primary and referred to the secondary? That is what we want to discuss. Okay, so because we want to discuss about the copper loss. So what is the total copper loss? Total copper loss in the copper, or this is generally written like the Cu loss. Okay, so what is the copper loss? Copper loss will be the primary current I1 square into R1 primary resistance plus I2 square into R2. This will be the overall copper loss, correct? And what do we know? We know that if I go by the like this two winding transformer, I know I2 by I1 will be equals to N1 by N2. So I2 will be equals to N1 by N2 I1. So I can replace it, right? So my PCU will be equals to copper loss. I'm just talking about the copper loss in the windings. So these are the windings where actually the copper loss will happen, right? So PCU will be equals to I1 square into R1. So I1 square into R1. So it is I1 square into R1. This will stay. This will be I2 square. I2 square is what? I2 square is N1 divided by N2 into I1 whole square into R2. Now is this something familiar actually? If I rewrite this, this will be I1 whole square into R1 plus this is I1 whole square into N1 divided by N2 whole square into R2. Okay, so if I take I1 square common, this will be R1 plus what is this? R2 into N1 divided by N2 whole square. This is basically referred, right? R2 dash referred to the primary. Okay, so this actually is the equivalent impedance seen from the primary. So this is equals to I1 square R1 R01. What does it mean actually? This actually means, what is R01? R01 is the winding resistance. This R01 is the winding resistance of both the coils. Refer to primary. Okay, winding resistance of both coils refer to primary. Okay, now same formula you can apply for the secondary as well. Let's say if I did not use this substitution, I wanted to do this, right? I wanted to do this, that instead of putting I2 equals to N1 divided by N2 into I1, I will do this. So PCU will be equals to, I will replace I1, that is equals to I2 into N2 divided by N1 whole square. Here I will have R1 plus I2 square into R2. So this will be equals to what? This will be equals to I2 square if I take common. This is what? N2 square into N2 square divided by N1 whole square into R1. So this is like the primary resistance referred to the secondary. So this will be actually R02. So this will be the winding resistance of both coils referred to the secondary. Okay. So yeah, that is what my R02 is, referred to the secondary. I hope you have understood this point. Now, this is actually the equivalent resistance, equivalent winding resistance. Now what about the per unit resistance, right? What will be the per unit resistance? So I want to calculate the per unit values of everything. Okay, I want to calculate the per unit values. So basically, I know that my copper loss will be same, right? Copper loss in the primary and the copper loss in the secondary, like power does not get transformed. If you remember, power does not get transformed, right? So if I want to write, so what is PCU in the primary and what is PCU in the secondary? So power will not, like whatever is the power. If I say the transformer is consuming a copper loss of 100 watts, it does not matter if you are talking with respect to primary or talking with respect to secondary. It does not matter. Okay, because power, it is independent, right? It is not dependent on which side I am in. So PCU1 is actually I1 whole square into R01 and PCU2 is actually I2 whole square into R02. So from here I get a very important relation, like you could have understood as well, that R01 will be equals to I2 by I1 whole square into R02. So I2 by I1 is N1 divided by N2 whole square into R02. So if you want to refer any impedance, same formula we are using, right? I wanted to refer the whole impedance, resistance, winding resistance in the secondary to primary. So what I have to do? I have to multiply by the number of turns in the primary divided by the number of turns in the secondary whole squared. Okay, so very simple, very simple. Just using the same referring concept. Okay, just using the same referring concept. So now let's discuss about one more thing known as the per unit copper loss. What will be the per unit copper loss? How do I find out the per unit values? So let's discuss. So what is my full load copper loss? CUFL, full load copper loss. It will be I1 full load, that is rated current, when the rated current will flow, I1 FL whole square into R01, no, so not R01, sorry, into R1 plus I2 FL whole square into R2. Okay, so this can be rewritten, right? So this can we convert it. That is what I am trying to think. PCUFL I2 square FL R1 plus, yeah. Okay, this is my full load copper loss. Now the copper loss at any load, right? What is the copper loss? Copper loss at any load. this, right, can be rewritten if my I can rewrite this as I1 square FL into R01, all of the winding resistance in the primary, or I can write this as I2 square into FL into R02, whatever suits you, right? Either way will work, both are same. Now what is my FL basically? FL basically is the full load I rated. I rated will be basically the S base rating of the transformer, S rated kVA rating divided by the voltage rating, that is a V rated. Okay, this is what my I rated is. So this is the current. So if I say that what will be the per unit copper loss, so what will be the I1 per unit? Like this we have already discussed, basics of per unit we have already discussed in chapter 0. So I1 pu will be what? I1 pu will be simply the actual value of I1 full load, whatever is the actual value, divided by the I1 rated or the I1 full load. I1 full load also works fine. Okay, and your I2 pu will be I1 divided by I2 full load. So I2 divided by I2 full load, correct? So these are the values. Okay, so if my what do you say, if my I1 actual value, I1 value is IFL, so what will be the per unit of I1? What will be the per unit of I1? So I1 pu will be what? So here I will replace, instead of I1 I will replace I1 full load, so it will be replaced with I1 full load. So this will be I1 FL divided by I1 FL, so it will be 1 only, 1 pu. Okay, 1 pu. So if I replace at full load, what will be pu FL? I want to calculate what will be pu FL. Okay, that is what I want to calculate. So it will be basically equals to what? My PUC, if I convert it with like my PUCL, sorry, PUFL in absolute values is I2 I1 whole square into R01 or I2 whole square into R02. So if I want to write the absolute values of PU, or sorry, the per unit values, right? PU's FL per unit. If I want to write it in terms of per unit, so it will be what? It will be like, it will be what is the rated value, right? Rated value is I1 FL. Here instead of I1 there will be I1 FL square, correct? And this R01 will be there. So this is the PU FL, right? Sorry, I2 also, this will be I2 FL whole square, correct? Okay, so this value will be basically now if I want to find out per unit full load copper, so it will be basically what? It will be I1 whole square into R01, correct? Like actual value upon the full load value. Full load value will be I1 FL whole square into R1. Okay, so this is the per unit values. I'm just thinking, am I doing anything wrong? That's what I'm thinking. R01 will not change, right? R01 will be same only. Yes. So PUFL, if I1 is I1 FL, then this will automatically get cancelled. It automatically gets cancelled. Yes. So basically, my, sorry, not full load copper loss, my copper loss in per unit, right? It will be equals to basically I1 divided by I1 FL whole square, correct? So what is I1 by I1 FL? I1 by I1 FL is I1 pu basically. I1 by I1 FL is I1 pu. So it will be basically equals to I1 pu whole square. Okay, so or same thing you can do for the secondary as well. It will be equals to I2 pu whole square, because in per unit, right, it does not matter actually. In per unit, the if I am in the secondary or primary, it does not matter. Okay, it automatically gets converted. Okay, now if, of course, if it is full load, so what will be the value in per unit of full load copper loss? So it will be 1 basically, because I1 PU will be 1, right, at full load, so that's why it will be 1. Now what about RO1 and RO2? What is the per unit value of RO1 and RO2? That is what we have to calculate. Okay, so what is RO1? R1 is basically R1 plus N1 divided by N2 whole square into R2. What is the base of resistance? Base of resistance will be V rated, V base upon I base, correct? So I am in the primary, so it will be basically what? It will be V1 upon I1, correct? This is my base, or you can write, yeah, this is my R base, right? V1 rated upon I1 rated. All right, I can write this in terms of not I1, in terms of the basically kVA rating. So it will be S rating divided by V base, V rated. So this is S divided by V rated. So it will be actually equals to V1 whole square divided by S, right? Because S is in the secondary primary, kVA rating is same, it does not change. Also this can be written as R base can also be written as V2 whole square divided by S, right? The rating of the transformer. Okay. So now I have to actually convert this into per unit. How do I convert this into per unit? That is what I am thinking. So in per unit, right, I have to simply divide this by its R base. So this will be R01 divided by its R base. Okay, that will give me the per unit value. This will be R01 per unit. So this will be equals to R01 is equals to R1 plus N1 divided by N2 whole square into R2 divided by the base. So base is I will choose now V1 divided by S. Okay, is it a good thing to choose V1 divided by S? That is what I am trying to think. Okay, V1 whole square divided by S. So what I can do, this is my RO1 PU. This expression is my RO1 PU. So I want to convert this expression. What I want to do, I want to convert this expression. So I want to take N1 by N2 whole common. So if I take N1 by N2 common from this will be N1 by N2 if I take common. Okay, N1 by N2 if I take common. So N1 by N2 whole square if I take common, this will be N2 by N1 whole square, N2 by N1 whole square into R1 plus plus R2 divided by V1 whole square divided by S. Okay, now what I will do, this relation also I know, right? So that is my V1 divided by V2 is equals to N1 divided by N2. So I can write my V2 is equals to N2 divided by N1 into V1. So that is actually what I will do. So this, right, N2, this if I take in the denominator, this will come out to be, this is RO2. The winding resistance referred to the secondary divided by, this will go in the bottom. So this will be N2 divided by N1 into V1 whole square divided by S basically. Okay, now what is this? What is this value? This is V2, right? This is simply V2 because this is V2. So this is actually RO2 divided by this V2 whole square divided by S. Now if you see, this is what, this is simply R base, right? This is R base. So this is RO2 upon R base. So what is this? This is RO to PU. So from here we get a very good relationship that my RO1 PU is equals to RO2 PU. It does not matter which side you are in, the winding resistance, overall winding resistance in per unit will be absolutely same. It will not change at all. Winding resistance will be absolutely same. It will not change at all. Okay. Another point to note here is this was the full load per unit copper loss. Okay, just hold on a second. So the per unit copper loss, right? Per unit copper loss will be actually, okay, I made a mistake here. Okay, sorry. This is not RO1, right? This is not RO1 actually. This is basically R base. So I have to divide by the R base actually. Okay, my bad. So this is actually not correct. So if I divide RO1 divided by R base, what will this be? This will be RO1 PU. So I was making a mistake here, sorry. This, right, this is simply I1 divided by I1 FL whole square. So this will be there, and here, right, I am dividing RO1. I will not divide by RO1 only, right? I will divide by the base. What is R base? R base is here, right? So actually this equation will be what? This is simply RO1 divided by R base. This is RO1 PU. So sorry, I made a mistake there. So this will be actually here RO1 PU also will be there. Sorry. So RO1 PU also will be there. Okay. Same thing will happen for the secondary as well. That so the expression gets converted. This is I1 divided by I1 FL. So this will be I1 whole square PU into RO1 PU. I made a mistake here. Here a RO1 PU also will be there. R1 PU also will be there, and this will be same for the secondary as well. So this will be RO2 PU basically. Okay, I made a mistake there, sorry. RO2 PU. Now the interesting fact is, if it is full load, so if it is full load, that means my I1 PU will be 1, my I2 PU will be 1. From this equation also you can prove it, that if it is full load copper loss, full load per unit copper loss, it will be equals to RO1 PU, or it will be equals to RO2 PU. So RO1 PU and RO2 PU are also same. From this equation also you can prove. Okay, so the full load copper loss will be RO1 PU or RO2 PU. Okay, in per unit. I am talking in per unit. Okay, now let's discuss the per unit value of drop. So this was about the winding resistance. So this was about the winding resistance. Okay. Okay, and this was about the copper loss. So I can say that what about the voltage drop in the resistor? So what is the voltage drop? So the drop in primary, it is equals to what? It actual value is I1 into R1. Correct. The actual drop in the primary is I1 into R1. So what will be the per unit voltage drop? What will be the value of the per unit voltage drop? So the per unit voltage drop will basically be equals to drop PU. It will be what? It will be this actual value I1 R1 divided by the V rated. Very simple, V rated. Okay. So what is this? What is this actually? At full load, what will happen? Because we want to discuss at full load. Okay. So if it is full load, right? So at full load, my I1 will be equals to I1 rated. Right. So my V drop actually becomes per unit value of V drop actually becomes I1 rated upon V rated. all this I'm discussing in full load only. I'm discussing in full load only. So this is actually equals to, into R1 is also there. So this is actually equals to R1 divided by basically R base, right? Or Z base, whatever you want to say. So this will be basically R1 PU. Now this is the drop in the primary. What is the drop in the secondary? What is the drop in the secondary? So similarly, if you do the drop in the secondary, right? V drop 2, drop in the secondary coil. So voltage drop in secondary will be equals to simply the drop. What is the drop? Value of the drop? It is I1, sorry, it is I2 into R2 divided by V rated, V2 rated. So this was V1 rated actually. This was V1 rated and this is V2 rated. So this will be V1 rated. Okay. So from here directly I can say like V drop secondary, right? V2 PU, V drop 2 PU will be equals to the at full load it will be simply R2 PU. Similarly, right? Same thing. So what will be the overall drop? What will be the total drop? Both in primary and secondary. So total drop will be what? At full load. All this I am deriving at full load. So that's why I don't believe in formula derivation. I just believe in like actual concepts. But sometimes we have to teach this as well because everyone else also teaches. And if this is not present in my notes, you guys will complain. Okay, but trust me, this will not be required. Main thing is the concept. Okay, this concept will be required. So all this should like I have to do because other educators do it. So total drop will be equals to the V drop 1 PU at full load. This is at full load, right? V drop 1 PU plus V drop 2 PU. Okay, so this will be basically R1 PU plus R2 PU, and it makes sense as well. So if in actual load, in actuality, what is the overall drop? So actual value of the overall drop, actual value of the total drop, actual value of the total drop, V drop will be drop across the primary, that is I1 into R1 winding resistance plus I2 into R2. So I have to just divide this by the V rated, that will give me the overall per unit. So instead of doing all those business, I can directly write it, right? I1 R1 plus I2 R2 divided by V rated. So this actually comes out at full load. At full load, this equation comes out to be, because I1 will be I1 rated. So basically what happens, this becomes V drop PU. This is PU, right? This is per unit value. V drop PU will be equals to R1 PU plus R2 PU. Okay, so this will be my answer basically. Now what is R1 PU plus R2 PU? If you remember that we derived here one thing, that actually R1 PU, right? R1 PU is actually R1 plus R2 PU only. R1 PU is actually R1 plus R2 PU. Have I derived it? I have not derived it. Okay, I have to derive it. Okay, so basically, right, this is my R1 PU. R1 PU is this. This is my R1 PU. So this I can further rewrite. What I can do is I can divide this, right? So let me discuss this as well. I have not discussed that. I have told you that R1 PU and R2 PU are same, but I have not discussed about R1. What is R1 PU equals to? So this is my value, right? R1 PU. So this, right, I can rewrite R1 divided by V1 square divided by S. What is V1 square divided by S? That is simply, this is actually Z base. Sorry, this is not R base. This should have been Z base. Okay, this will be Z base over here. So this will be R1 divided by Z base plus, now n1 by n2 whole square is there. Can I take it in the bottom? Can I take it in the bottom? If I take it in the bottom, this will be R2 divided by V2. This is Z1 base actually, and this is what? V2 whole square divided by S. So this is what? This is actually Z2 base. This is actually Z2 base. So ultimately this is equals to R1 PU plus R2 PU. So basically my RO1 PU is equals to RO2 PU is equals to R1 PU plus R2 PU. What is R1? What is R2? R1 is the primary winding resistance. R2 is the secondary winding resistance. R2 is the secondary winding resistance. So this I can actually replace here. So this, my full load drop, actually there is a formula, very famous formula. Full load drop will be equals to R1 PU. My copper loss also, full load copper loss also will be equals to R1 PU, or it will be equals to RO2 PU, because both are same only in per unit. So very famous formula. No need to remember, just I have to derive these things, because in the exam also, in the exam hall also, you should be able to derive it. How many formula will you remember? It's impossible for you to remember this many formulas, but as I am deriving in front of you, you should also be able to derive the formula. That is the most important point that you should understand. Okay, so basically conclusion is, in per unit, transformer behaves as a 1:1 turns ratio. Transformer behaves as 1:1 transformer. Doesn't matter what is the turns ratio of the actual transformer, but in per unit, the transformer behaves as a 1:1 transformer. That means basically it does not matter in per unit, referring voltage, current, impedance will remain same. Okay, if I refer voltage, current, impedance from one side to other, it will remain same, because turns ratio is 1:1, right? Turns ratio becomes 1:1. So 1:1 whole square is 1 only, so it will not change anything. So turns ratio is 1:1 in per unit only. So this will be used hugely in power systems. Okay, so as turns ratio is 1:1, this will be hugely useful in power systems. So we will actually solve many questions in power systems using this per unit value concept. Okay, so that was it basically for this lecture, and in the next lecture, whatever we have discussed till now, we will solve few assignment questions on those. Okay, I hope you have enjoyed. If all the concepts are clear, I know there might be a bit of doubt in the phasor initially, but I have tried to clear everything up. Okay, so I hope you have enjoyed this lecture. If you did, make sure to hit the like button, make sure to comment down below on the video, whatever you feel like. Okay, if you loved it, let's say love you. Okay, not literally, but you love the concept, and if you hated the video, then you can say I hate you. Okay, not literally, but the concept, I hated the concept that you explained. Okay, so yeah, that's it from my end. I will see you in the next lecture. Until then, happy learning.